Hello, during this session I'm going to be explaining the kinetic model of an ideal gas. Much like the animation you can see on the screen in front of you, the kinetic model of an ideal gas is a method of thinking about a gas in the context of it being small particles bouncing around that allows us to join or see links between the microscopic actions of a gas and the macroscopic outcomes which we can measure and record relating to pressure, volume and temperature. So thinking about a gas in this form is useful for that connection, and particularly an ideal gas. So we're talking about an ideal gas at the end of this, but as I said, it is a model for an ideal situation. There are some extremes where this breaks down. I'll talk about that at the end. So, the kinetic model of an ideal gas. There's a set of assumptions which are made for this kinetic theory of gases. Assumption number one, that the molecules behave as if they were hard, smooth, perfectly elastic spheres. So that means the collisions are perfectly elastic and no energy is wasted. The molecules are in continuous, rapid, random motion. Okay. So they're moving around and bouncing around, and this is random. The average kinetic energy of the molecule is proportional to the absolute temperature of the gas. This is one of the important driving forces because it links together the actions of the molecules and temperature, and therefore their actions as temperature changes has an impact on pressure and volume. Molecules do not exert any appreciable attraction on each other. Okay, so this is to recognize that for this to work, there's no attractive forces between the molecules. The volume of the molecules is infinitesimal when compared to the volume of the gas. So these are very, very small compared to the volume of the gas itself. The time spent in collisions is small compared to the time between collisions. Just like the model we've seen beforehand, they'll collide and move apart. And most of the time they're moving around without any interaction with other particles. Now, make it clear, because the collisions are perfectly elastic, there's no loss of kinetic energy as a result of the collisions. So therefore, collisions don't have an impact on temperature, and collisions which naturally occur don't have an impact on temperature. All these things are wrapped together very, very carefully. So make sure that you're aware of those implications. So these are the assumptions of the kinetic theory of gases. One of the key things here is if we look at these particles, I've highlighted there's a relationship between the average temperature, the average kinetic energy of the particles and the temperature. So the average kinetic energy of molecules is proportional to the absolute temperature of the gas. That means if temperature is 0, in theory the particles will be not moving in any way at all. And as temperatures increase, the average kinetic energy of the molecules increases, and we see the particles bouncing around more and more. Now remember, this is the average kinetic energy. We might have noticed, or I might have noticed early on, there should be a distribution of all the particles from going very, very slow to going very fast, and we have an average value. Now, if we put this into calculation, the kinetic energy average is equal to 3/2 Boltzmann's constant times temperature. This is per molecule, and as we know, Boltzmann's constant is equal to the universal gas constant divided by Avogadro's number. So 3/2 universal gas constant divided by Boltzmann constant times 2 is equal to the kinetic energy average per molecule. And more importantly, the average kinetic energy per mole is just multiplying this number by Avogadro's number. So we end up with 3/2 times the universal gas constant divided by T is the kinetic energy per mole of gases. So that's an important link there, and there's a calculation, and these are some values which you'll appear on your data sheet. So I mentioned how there's a kinetic theory model. I described that, but this only works for an ideal gas. What's an ideal gas? An ideal gas is a gas that theoretically obeys all the gas laws and thus fits the ideal gas equation exactly. So this is the equation of state for an ideal gas exactly. That's all well and good, but real gases don't quite work like that. Real gases conform to the gas laws under certain limited conditions, and this is basically the middle bit and not the extremes. This is because they condense to liquids and then they solidify if the temperature is lowered too much. Furthermore, there's relatively small forces of attraction between the particles of a real gas. Again, and that contradicts one of the assumptions we make for the kinetic theory. But nevertheless, on the whole, gases behave just like the ideal gases. It's only at the extremes do we see some issues with real gases being different to ideal gases. So that's my quick overview of the kinetic theory of an ideal gas.